Hello, Honors Chemistry, and welcome to Chapter 7, 7.6, Precipitation Reactions, where we're going to take the skills you learned in terms of how to name compounds from Chapter 5. We're going to layer in your skills with balancing reactions, and now you're going to be able to take a pair of reactants and figure out what the products are just based on your own skills. Very nice, huh? All right, so first of all, what is a precipitation reaction? Going back to what we talked about at the beginning of the chapter, a precipitation reaction is one that produces a precipitate, right? Where we take two aqueous reactants, we mix them together, and upon doing so, a new solid is formed on the product side. Yes, a new solid is formed on the product side. So here, if we take aqueous potassium iodide and mix it with some aqueous potassium nitrate, what ends up happening is we form some solid lead iodide, right? We do also have this other product, potassium nitrate, which is aqueous. And if we think about what that means, right, again, we have an ionic compound that is in water, right? Because, let's dissect this, right? Anytime we have aqueous reactants, that means, right, that water is present, yes? Because by default, if we say something is aqueous, we mean that it is dissolved in water, right? So while potassium iodide is the key component, right, water is the background component, right? Same thing with our aqueous lead nitrate, which means that as we assess what happens on my product side, we already know that water is in the background, and we understand that based on our solubility rules, potassium nitrate is soluble, right? And there's water present, therefore it will be aqueous, okay? So we have our new solid and we have our ionic compounds. Now, again, using our solubility rules, we know that if I take some potassium iodide aqueous and mix it with some sodium chloride aqueous, right, there will be no reaction, right? Or we might symbolize it this way, right? In that the products formed are all aqueous, yes? The products formed are all aqueous, which means that when we look at my beaker, what do we observe? Correct. Nothing, right? We see no change because nothing of note has happened, right? We had some aqueous ions, and on the product side we have, again, all aqueous ions, okay? All right. Now, how do you know what the products will be, right? Here is where our understanding of ionic compounds comes into play, okay? So you already know that an ionic compound is composed of a cation and an anion, yes? All ionic compounds are composed of a cation and an anion. So in a precipitation reaction, for our purposes anyway, what we're going to be looking at is two ionic compounds, yes? We'll look here. I have Ki, PbNO3, two ionic compounds. Ki, NaCl, two ionic compounds. So then, I'm going to take those two ionic compounds, and all I'm going to do, and you choose a way to memorize it that makes sense to you, I like to say that my cations will switch places, yes? My cations will switch places. And upon doing so, I end up with two new compounds, right? So, if my cation here and my cation here were to switch places, right, that means my lead is now stuck to my iodide, yes? Means my potassium is now stuck to my nitrate, right? And you'll see that those are the products we form, yes? We still have to follow all of our chapter 5 rules, right? The charge of potassium is still 1, the charge of nitrate is still -1. That's how I'd write that formula, right? I can backtrack and figure out the charge of lead here, just like we learned how to do back in chapter 5, and use that to figure out how to write this formula, okay? Same thing over here. Potassium is my cation, sodium is my cation, and they will switch places. Now, I would have KCl and NaI, but again, going back to our solubility rules, both of these are aqueous, which means that I still have the same 4 ions floating around in solution, which is why this gets labeled as no reaction. Yes? Okay. And so these are just the figures from your book that sort of make that more clear, right? At the microscopic level, so Ki looks like that, lead nitrate looks like that, right? At the instant of mixing, now all of my ions are able to come into contact with one another. And so here you'll see that my cations are switching. So now my potassium has the opportunity to interact with the nitrate, right? And the lead has the ability to interact with that iodide, producing one insoluble compound, right? Which makes us a new solid, right? We'll talk in chapter 8 about the quantitative aspects of this, right? Like how much lead iodide do we form? How much potassium is left? How much nitrate is left? Is there anything else also left, right? That all comes to play in chapter 8. Right now, we're just talking about the qualitative aspects, which are what do we produce, right? And what can we expect to see because of that, right? Now, if I know I'm going to produce a solid based on my solubility rules, I know that visually, I should expect to see a precipitate, right? I should expect to see cloudiness. I should expect to see something that says new solid is present, okay? You cannot predict, right? For example, you would not know to predict that it would be a bright yellow color change, right? But you should be able to predict that solid means new, it would become cloudy. There would be something on the bottom, something that says solid was formed, right? Here, you would be able to predict nothing, right? As in like you would see nothing, nothing would happen. Okay, so let's go ahead and practice with a couple of these, right? So, like I said, step 1, we're going to have to write down our reactants. Step 2, we'll figure out switching the cations, and then we will go ahead and balance. So, and apply our solubility rules. So we have potassium hydroxide, right, which is KOH, and it's aqueous. And we have some nickel 2 bromide, and again, that is the charge of my nickel, right? So NiBr2 aqueous. And so, like I just said, what's going to happen is we are going to have our cations switch places. So cation, and they will switch places, okay? And so if they switch places, now my potassium is going to be stuck to that bromine. Potassium has a charge of +1. Bromine has a charge of -1, which means I only need one of each, right? And for my other compound, right, nickel has a charge of 2, and it still will, so nickel hydroxide, because hydroxide has a charge of -1. Now we're going to layer in our solubility rules, right? So potassium is a group 1 compound, which means that this is aqueous, right? Nickel hydroxide, if you remember, hydroxides tend to be insoluble, which means we've just formed a precipitate, yes? So then we'll go back and balance. It says that there are 2 hydroxides here, which means I'll need a 2 here, which means I'll need a 2 here, and then it's balanced, okay? And in terms of visuals, what we should expect to see is I will see clear, colorless. When I mix them, I form a new solid, yes? And this will just stay in the solution. Yes, does that make sense? All right, next reaction. It says we have solutions of ammonium chloride, so ammonium chloride, aqueous, and iron 3 nitrate, so FeNO3, aqueous, are mixed. So again, right, we would look at this and say, taking back one step, right? 2 ionic compounds. We're going to switch the cations, right? So let's go ahead and ID the cations. Here we have ammonium and iron. So we'll go ahead and switch those, which means that now my ammonium is going to be stuck to my nitrate, and ammonium is +1, nitrate's -1, so we need one of each. And we have iron, which has a charge of 3, stuck to chloride, which has a charge of -1, so there we get that. Now let's go ahead and apply our solubility rules, right? Which says ammonium and nitrate, for that matter, always soluble, so this would be aqueous. FeCl3, chlorides, right, tend to be soluble. Iron is not an exception, which means that this is no reaction. And you can, because obviously you will need to predict the products, and then I would just put a big old X through the arrow and call this one done. Yes? All right. Next up, it says we have potassium sulfate, right, which would be K2SO4, aqueous, and strontium nitrate, SrNO3, 2, aqueous. And again, right, 2 ionic compounds, identify the cations, switch the cations, and then we'll have potassium will now be stuck to nitrate. Potassium has a charge of +1, nitrate has a charge of -1. That formula is correct. Strontium has a charge of +2, sulfate has a charge of -2, so that's correct, right? And then now we'd apply our solubility rules, right? Potassium is group 1, always soluble, this is aqueous. Strontium, sulfate. We would think, sulfate's always soluble except for calcium, barium, strontium. So this is a solid, right? So now we would have to go back and balance, and we would see that that's as simple as putting a 2 right here, okay? And then in terms of what we'd see, right, we have a clear colorless solution mixed with a clear colorless solution, which then produces a new solid, right, or we would see some cloudiness or something, right, and then one other product that is still in the present but just in the aqueous state. Yes? All right. So again, we would see two ionic compounds. We will switch the cations, and then we will use our solubility rules to decide if we form a precipitate or not, right? And then we would balance, right? And note that embedded in all of that is our ability to take Chapter 5 and write correct formulas for each of the species at hand. All right. This is section 7.6 on precipitation reactions. Next up, we'll learn how to add a little bit of detail to these. All right. Thank you for listening. Be good, and I will see you soon. Bye.